So last time we covered that rotation by pi over 2 radians counterclockwise is a linear transformation. We had a drawing for that. Hopefully you can see that I could have rotated by any amount of degrees, clockwise or counterclockwise, and this property of linearity would still hold. The picture would just look more skewed, a bit look longer, different, but all the arguments would still work the same. So where do matrices come in? Well, here's how they come in. Here is how we decided that if I want to rotate by pi over 2, the vector 3, 2, I could just rotate the constituent components and then scale them up accordingly and add them together. This is linearity. So just to break it down a little more, the rotated version of 1, 0 is 0, 1. And the rotated version of 0, 1 is negative 1, 0. And let's just interpret what these things are here. What is the interpretation of 0, 1? Let's not forget it's where 1, 0 got mapped to. So, and these 1, 0 and this 0, 1 here, keep in mind, these are like our coordinates. They're our basis vectors. It's the unit vector in the x and the unit vector in the y. So these are all, these are essentially our basis vectors, our fundamental coordinate system that we're working with. And 0, 1 is where the first basis vector got mapped to by our rotation. So this 0, 1, think of it as where the first basis vector was sent. Where the first basis vector was sent. Well, what's negative 1, 0? That's where the second basis vector got sent. Where the second basis vector got sent. So these two vectors here, they're a property of the transformation. They're sort of like the cipher or the key that tells you what this transformation will do. Because now I know what it does to the basis vectors, I can always do this trick of linearity, scale it accordingly. I'll be able to know what it does to any vector. I'll explain that more later. What is that 3? That 3 is just this 3. So this 3 and this 2, these come from the vector I wanted to rotate. Come from the vector I wanted to rotate. So think of those as like the inputs. It's essentially the input vector. And what matrix vector multiplication does is it sort of puts those two into nice categories. These two vectors are sort of inherent to the transformation. So they get to go together into a matrix. So 0, 1 is the first column. Negative 1, 0 is the second column. So the way to read this matrix is exactly how you are reading it here. The first column of a matrix is where the first basis vector was sent. The second column is where the second basis vector was sent. And thus, in this matrix, I've sort of encoded the entire transformation. Because as this expression tells us, if I want to rotate some arbitrary 3, 2, all I have to know is what it did to the basis vectors. Then I just put the 3 and 2 up front and just add it together. So in a way, that's why they say the matrix encodes the whole transformation. Encodes the transformation. So in a way, this is sort of like the function t in matrix form. And the 3, 2 came from the 3, 2 I wanted to rotate. This is the input stuff. So that gets stuck afterward on the outside. This is the input vector. So the rotated version of 3, 2 equals this matrix vector multiplication. And there are some natural reasons to write it this way. First of all, it's nice that I can just look at a matrix and I sort of know everything I need to know about the transformation t. I know where it's sent the first basis vector, I know where it's sent the second basis vector, and that's enough. And then it's nice to have the input vector all alone on the side. Notice the the nice resemblance this has to how we write functions in general. It's always, like an f of x, right? That's how we write functions. The function and then the input. The function and then the input. It's really quite natural. Okay. And if you're doing linear algebra, especially for the first time, and you're looking at matrix and you're looking at this kind of stuff, read it this way. Don't look at the matrix and see 4 numbers. Look at it in terms of columns. The first column is where the first basis vector was sent to. Second column is where the second basis vector was sent to. And the thing that comes after is the input for the transformation. So that when you do the matrix vector multiplication, which is just this, keep in mind, these two are defined to be the same thing. This is a notation for this. The act of doing that matrix vector multiplication, turning this back into this, now you can see is exactly how we do. It's exactly how we do this rotation. We had done it in the previous video. So take a moment to let that sink in on your own. And just to emphasize the point that if I know this, I know what the rotation does to anything, we can do a general case, which is if I want to rotate a totally arbitrary vector AB, okay? Well, the linearity tells me I can write it as A scaled r power 2 times 1, 0 plus B r power 2, 0, 1. This is just linearity, distributing the function in. Well, r power 2 of 0, 1, we established, plus b, and 0, 1 got turned into negative 1, 0. Now, I can write this in the matrix vector multiplication. First column is where the first basis vector got sent to. Second column is where the second basis vector got sent to. And the input vector goes on the end here. Keep in mind, these two are the same literally because we defined it so. This is just notation. So, I can use this, I can use this. It's all going to turn out to be, do it, minus b, a. So, I've taken an arbitrary vector ab. If I rotate it power over 2, I get negative ba. And, I didn't need the matrix and vector, right? It's not necessary for me to compute this. I can go from here to here to here, and this I can just compute to be this. But this is a more compact way to write this that clearly says this is the transformation and this is the input. It sort of separates it out into these two nice bits. And that's essentially one of the motivations behind matrix vector multiplication.